Now we can use this band theory to explain, briefly, why metals conduct very well, semiconductors conduct a little bit, and insulators essentially don't conduct at all. In an insulator, we have one band that is essentially completely full. That's the outermost band with the outermost electrons. It's called the valence band. And then the next energy level is completely empty, and there's a large energy gap between the valence band and the conduction band. It's called the conduction band. So large that thermal excitations would almost never make electrons make the jump up here where they can conduct. So as an example, in, I believe it was diamond they gave, this energy gap is about 5.5 electron volts. And so the probability of an electron jumping from here to here is e to the negative change in energy over kT. At room temperature, kT is approximately 1/40th of an eV. So this is e to the negative 5.5 eV divided by 1/40th of an eV. That is e to the negative 220. And if we take that 220 negative and the exponent, inverse of the natural log, that's about 3 times 10 to the negative 96. It's never going to happen. It's simply too small of a probability. Now, in a metal, the electrons fill up to the point that we have the lastmost energy level, the valence band, half full, or at least partially full and not completely full. That means that electrons down here can easily jump up into this conduction region in the same valence band. They don't have to get up here to a new band. They only have to make the microscopic energy jumps within a single band. So it's tremendously easy for an electron to get up there and to conduct freely. As a result, metals are tremendously good conductors. Now, in between, we have the case of a semiconductor. Like an insulator, a semiconductor has a valence band and a conduction band. And the valence band is completely full, while the conduction band is completely empty. What's different in a semiconductor is that this gap is much, much smaller. So, for example, in silicon, that gap is on the order of about 1.1 eV. What does that mean? My probability of having an electron jump up from the valence to the conduction band is e to the negative 1.1 times 40, or 40, or essentially 44. Well, e to the negative 44 is still very small, but it's not impossibly small. If I take 44 negative inverse of the natural log, that's 7 times 10 to the negative 20, which means about 1 out of every 10 to the 20 atoms will have an electron excited from the valence band into the conduction band. It's still rare. These are not very good conductors, but there are enough electrons that do make the jump that we will occasionally get some conduction happening. A typical sample will be at least 10 to the 20, if not 10 to the 22, 10 to the 23 atoms, and as a result, that actually has many, many conduction electrons available. Also, I should point out that when we do excite an electron from the valence band into the conduction band, not only does the conduction band have these electrons, which are relatively free to move and can therefore move from atom to atom to atom, but the valence band now has a few little holes in it. And because there's this hole here, place where an electron isn't, then the electron right next to it can jump into it, leaving the hole right here. And an electron can jump into that, leaving the hole here. It's easier to describe this in terms of the hole drifting opposite the direction that the electrons drift in the conduction band. But they both contribute to the conduction of electricity in the semiconductor. So we don't have electrons totally free to move, but we do have a few that get excited from the valence band into the conduction band where they can conduct, and that leaves a few holes in the valence band, and those holes can also conduct.